Hello everybody, how are you? Hope all of you are doing well. So in today's video we are going to discuss about the line coding. This is that line coding that obviously everybody have to perform in our laboratory. Okay, so this video will be very much helpful. If you watch this video from first to last, you will learn much more knowledge you will gain about the laboratory of line coding. Again, I am telling, just like my past videos, whatever I have already told you, that is, this video is just for laboratory purpose. I am not going to show you the detailed calculation and analysis. I am just going to give some basic knowledges, whatever the questions may be asked in your laboratory exam. This related knowledges I am going to give you. Whatever I am going to give you, that is more than enough to perform the laboratory experiment in the digital communication subject. And one more thing, this is the last video of digital communication lab, because this is the experiment number 6 in our syllabus. There are total 6 experiments. For among the 6 experiments, I have already made 5 videos for 5 experiments, and this is the last experiment number 6, that is the line coding. Line coding is very much interesting. Okay, so I am requesting you to kindly watch this video from first to last, because there are not so much content just like as my past videos. The content is very less, so I hope that I will end this video very soon. Okay, so without wasting now any time, let's jump into our video. See, first of all, anything, whatever we study, if you know that why are you studying that particular topic, why are you studying the particular subject, then the subject or the topic becomes very easy, right? So actually the subject is digital communication. Okay, in digital communication, whatever we do, we basically transmit our analog signal from transmitter to receiver, okay, or at a long distance in terms of digital pulses, right? That is nothing but basic funda of digital communication. That is the basic thing, that is the of this subject actually, right? So again, I am drawing the total things in the digital communication. What is that? See, our voice signal, we want to transmit our voice, right? That is voice signal. But remember, this voice signal, that is the MT, this is analogous in nature, right? Our voice signal is analog signal. Whatever we are studying here, we are actually studying the digital communication, right? So we have to convert this voice signal into some digital signal, okay, and this conversion is done by what? That is the sample and hold. The sample and hold circuit is used to convert the any time domain signal into a discrete signal, and we can say this is the M of KTS. That is, this is the sampled version of the analog signal. See, our signal or message signals is analogous in nature. Okay, to send it in the form of digital modulation, or to modulate the analog signal in the digital modulation form, to modulate the analog signal digitally, the first thing that we have to do, we have to make this signal discretized. That is, we have to make continuous time signal to discrete time signal, and that is done by sampling. Everybody know that. So after the sampling, several kinds of modulation techniques are there that already most of the people know. That is, one is modulation technique, that is PCM, right? In PCM, what is done? Quantization and encoding, you know, that is PCM. Another modulation technique is there, that is DM, delta modulation. Another modulation technique is there, that is ADM, that is adaptive delta modulation. Okay, and without this there are some other modulation that we also know, that is DPCM, that is differential pulse code modulation, HDM, that is sigma delta modulation, and etc. But most of the cases we generally use any of these three kinds of modulation, that is pulse code modulation, delta modulation, or adaptive delta modulation. And why this modulation has been done over here? Because through this modulation we have modulated the discrete time signal, that is in the discrete time form of this MT, of the message signal or the message signal. That is, we have converted the message signal into digital signal first, then we modulate the digital signal, and after modulation what are actually we transmitting? We are transmitting in the forms of zeros and ones, that is the digital data. And what this digital data contains, actually what is the base of this digital data? This digital data has been formed by the modulation, and the modulation is done by the sampled signal of the input voice signal. Okay, and this is the signal that we generally transmit via wire or wirelessly, whatever. Okay, and this is the total portion of the transmitted. Okay, before transmitting we do generally these things, these much things we generally do. That is, what is doing, we are doing, there is a continuous time signal, there is a voice signal. I am assuming that this is the sinusoidal signal. Okay, then here after sampling, what we get actually, if you use the flat top sample, then we get generally these kinds of signals. Okay, this is the flat top sample signal, and after from this sample, through encoding and quantization and encoding, we generally convert the sampled signals in the digital data. That is nothing but the digital modulation. Okay, this portion is actually the digital modulation. Okay, this is the portion of the digital modulation. And after digitally modulated, after the signal being digitally modulated, they are transmitted in the forms of ones and zeros. So this is the transmitted portion. Now in the receiving portion, there is in the receiver, what the receiver is getting actually, receiver is getting the same digital data that we transmitted, that is digital data. Okay, digital data means in the forms of same zeros and ones. Okay, same zeros and ones. And the first thing that we have to do, that is the demodulation. Here we did modulation, so here the first thing we need to do, that is the demodulation. So there are several demodulation techniques also, just like we can also demodulate through the PCM technique. Okay, that means decoding and detection. Okay, PCM, DM, the same techniques whatever we applied in the modulator, the demodulator circuit of this technique we can apply for demodulation. Okay, obviously whatever modulation we have used in the transmitter, the same categorized demodulator circuit we have to use in the receiver, right, to demodulate it. Okay, there are several other methods of demodulation also, that is DPCM and SDM, that is the sigma delta modulation, and so many are there. Okay, this is for the digital demodulation, right? This is the digital demodulation circuit. And after this demodulation, whatever we are getting, see, after this demodulation we are getting actually the received sampled version of the signal. So there may be some kinds of noises that may interfere the received signal. So I am not considering here that, because this is not main concern of the line coding. Our main purpose of the line coding that we are going to, I'm going to tell in a short, just hold your patience. That is, this signal, whatever we have received in the after the demodulation, is the same signal whatever we did after sample and hold a analog signal. This is the sampled version of the analog signal will again occur if we demodulate this digital data. Okay, so from this digital data we can use some filter method here. Okay, we can use some filter. Okay, across this is the digital data or the sampled signal. So after some filtering or some detection process, we can get back our message signal. Okay, or the detection filter or detection. Okay, detection, we can get back our message signal, that is the original message, that is M cap T. See, this message signal and this message signal is the same signal, that this is the analog signal. Okay, this is the analog signal. So these two message signals are same. The cap has been used because I want to recognize that, I want to mention that this capped version of the signals represents in the receiver circuits. Okay, so for transmitter circuit I haven't given the cap to identify that this is inside a receiver circuit. I have used a cap. This is just a notation, nothing more about it. Now the question, this is the total case of a digital modulation. So from where to where our digital communication is required. See, after the voice signal being sampled and discretized from here to here, that is until the voice signal is demodulated or the same signal has been got back in the receiver, we use the digital communication techniques. That means starting from this sampling portion in the transmitter, ending at the demodulation portion, demodulated version or the demodulation at the receiving session. This is the total path of the communication of or the digital communication, because everything is being in between these two paths is in the form of zeros and ones. Okay, now everything was okay. There is a now big problem. The problem is, suppose this is a channel, right? What is this actually? Here, from here channel starts. This is actually channel. That means through this channel, this may be wired or wireless, whatever, but through these channels our digital data, that is in the form of zeros and ones, is passed. Okay, and the same channel has been connected in the receiver also. Okay, this is the channel. Through this channel, what is passing actually? The zeros and ones that was encoded or quantized, after quantization encoded, whatever the modulation techniques we have used. After the modulation, the zeros and ones that were formed is being transmitted through this channel. Now the problem is, suppose a third person, want to access the channel. That is, if you want to see whatever the data is passing through the channel will be easily accessed by this third person. That means in one sentence I can say, this digitized data or if the message is very crucial, or in case of military purpose the message is very crucial, if the message is very crucial or important, that it is so important that it should not be known to some other persons or to some general person. So for that cases, if anybody want to see that whatever the data is passing through the channel, he can easily access the data. Okay, so the security of the data is broken, right? So that means whatever the digital, if anybody get the digital bits or the digital data streams, whatever is passing through the channel, then he or she can easily detect, or easily after some demodulation he can easily convert this digital data to the original voice signals, or he or she can easily use some demodulator circuitry to extract the original voice signals, right? So that's why here the question is, what we can do so that we can transmit our digital data through a channel as well as nobody can detect it. Okay, see, it is not possible to remove the channel, right? Somebody can think that if we can remove the channel, then nobody can access it. The channel must be always there, we can't do anything with the channel, right? So anybody can access the channel at any time. It is not possible to provide security at each and every corner of the channel. So there is the one way that through which we can transmit our digital data or the digital data bit streams through the channel securely. What is that? We can convert this digitized data. Okay, we can convert this digitized data in some form, in some other form, suppose, so that logically we can convert the digital data in some other form, so that if anybody can access the channel, he will see the converted data, but he will not be able to detect what the original data is. See, the green color signal is the original data. What we are doing here, we are converting this green color signal or the original data into some other database streams through some logical conversion or through some techniques, so that if anybody can access the channel, he or she will be able to see this converted data, and he will not be able to detect the original message, because original message signal, the corresponding database streams of the original message signal is now converted, right? That is completely changed. So from this changed signal, if anybody don't know what is the logical conversion used here, he or she cannot be able to detect what is the original message signal was. So securely we can transmit these converted data bit streams to the receiver. And what is receiver will do to get back the original signal? In receiver, nothing will be done. The same logical operation or same techniques that was used in conversion, using that same techniques, this will be detected in the receiver section. Using the same technique, the converted data will be extracted. From the converted data, the original data bit stream will be extracted. But the technique which was used in the transmitter and which will be used in the receiver, that is completely unknown throughout the whole channel. So any third party access is removed, because if anybody want to access the data, he or she will be able to know what is the database stream is passing through the channel, but he or she will not be able to detect the original message signal, right? So through this way we can transmit our secure data or the crucial message very easily. Okay, and this is the technique through which we can convert our original database streams in some other form, that is called the line coding. Okay, here is the requirement of the line coding. This technique is called the line coding technique. Here also, using this line coding at the transmitter section, we are converting our original data into some other form. Okay, so that any third party access cannot detect the original database stream or cannot extract the original message signal. Okay, but the same line coding which was used here, there are several types of line coding. These line codings are these, that is the NRZ, RZ. I will discuss it later. Several kinds of, several techniques of, several types of line codings are available in the market. The same line coding which was used in the transmitter section must be used in the receiver section to detect the original message. Okay, so this is the main thing why we use actually line coding, and where is the position of the line coding, where we apply the line coding in the communication total system, that is in transmitter section as well as in the receiver section, where we apply actually the main line coding technique that I have already told you. So what is line coding? Line coding is nothing but line coding. What is line coding? If anybody asks you a question, what is line coding? This is a technique where through which we can convert the original data. Okay, original data means their data must be in the digital form, that is the original data, okay, to some converted form, a coded form, where we can say, better to say, the coded form. The coded form data is completely changed, okay, through some logical conversion. This is done logical conversion. And these techniques of logical conversion is called line coding. We will see. Okay. Now I am going to discuss one example, and this is the same example that I have taken in the laboratory, so that you can match whatever the theory I will show you, each and everything the same in the practical purpose also. Okay, that is whatever I am going to do right now. Now I am going to consider a digital message signal. First of all, suppose there is a digital message signal that is 1100 1010. So this is not, this bit is not 1100 1010. This is the digital message signal, and message signal means this is actually the original data that I have already told you. This is the original data. Original data means we first converted the analog message signals in the discrete signal in the form of sampling. After sampling through quantization and encoding and several kinds of digital modulation technique, we have converted the sampled signal into a digital data, and this is the original data that is to be sent through the channel. Now, as we know that we cannot send this data through the channel, because if the data is very much crucial, that will be easily accessed any third party access, right? So what we have to do, we have to convert this data into some form, that is we will apply several line coding techniques on this data, and we will see how the original data will be converted, how the pattern of the original data will be changed, right? So we will see several techniques, several line coding techniques, and basically we will discuss here the 4 types of line coding techniques, though there are many number of line coding techniques in our theoretical syllabus, but for practical case, for performing the laboratory, 4 is enough. So now our main concern is to what? We are going to convert this original data into some form, so that from the converted waveform, see, listen to my words carefully, from the converted waveform or the line coded waveform of this main original data, anybody cannot detect what the original data was actually. That is, I will change the shape of the waveform itself, right? If anybody want to analyze, he will see the coded waveform, not the actual waveform. See, whatever the actual waveform we generally do, from 1 we generally, in digital we generally use the high pulse, right? from 0 we use the low pulse. In this way we continue in the digital digital electronics. We have already seen, right? From 1 we use high pulse, from 0 we use low pulse. So if this data we convert this data in normally, then what the data will be? This will be something like this, right? 1 1 0 0 1 0 1 0, right? This is the actual conversion or the actual data waveform, actual original waveform of the original data, right? Now we cannot transmit this waveform. What we are going to do, we are going to change the shape of the waveform into some other form through some logical conversion, through some line coding techniques. Okay, if we can change the waveform shape, suppose if for 1, suppose we are transmitting for where, from 1 for 1 we are transmitting the 0, again for the next one we are transmitting 1, then it is not possible to detect for any other person that what the original waveform was. If we convert this, if we change this waveform into some other form, this is not through some logical conversion techniques, that is the line coding technique. If we change this original waveform into some other waveform, so it is not possible to detect the original waveform from the converted waveform. After conversion you will understand it more clearly. So let me draw it. What are we going to do? First of all, I'm going to draw the original waveforms. So our original data is what? That is the 1 1 0 0 1 0 1 0. Though I have taken this data randomly, but using this same data we will perform the experiment. I have performed already the experiment in the laboratory. Okay, I will show you after this theory class. Whenever I will show you the waveform, that whatever we have got for different kinds of line coding techniques, you will be able to match the waveform clearly. Okay, so that's why the same data that I have already taken, that I used in the laboratory, I have taken the same data for understanding in the theoretical. So what is this actually? This is the digital data. Digital data means this is our original data. What we don't want, we don't want to transmit this data, right? We want to convert this data through some line coding technique. So our first line coding techniques just come into the picture, that is bipolar NRZ or bipolar non-return to zero. Unipolar or bipolar, sorry. NRZ, I have already written NRZ, that means it is non-return to zero. Okay. Now, what is the basic difference between unipolar or bipolar that you should know first? That is, I am mentioning here. That is very easy. If I tell you that write 1 and 0, we can write 1 and 0 into two categories, in two types. This is a 2-bit data, right? 1 0. We can write this 1 and 0 into two types, in two categories. That is, for 1 we can use the positive voltage, and for 0 we can use the 0 voltage. Or we can also use some other kinds of representation. That is, for 1 we can use positive voltage, but for 0 we can use negative voltage. Okay, that means if we use a single sided, that you can see that the waveform that will produce in this manner will be the upper side of this 0 line, 0 volt line, right? So that's why it is called the unipolar. That is, it is unidirectional. Unidirectional means it has distribution, the waveform is distributed only the upper side of the zeroth line. That's why it is called the unipolar. Okay, and for this case you can see the waveform is distributed for the same code, that is 10 code. For the same code, the waveform is distributed in the both side of this 0 volt line. So that's why it is called the bipolar. Okay, what is unipolar? Unipolar means the waveform is distributed only any one side of the 0 line. Okay, that's why it is called the unipolar, because it is unidirectional or unidirected waveform. And for bipolar you can see that the waveform is distributed in upside and downside of the 0 waveform. So that's why it is bidirectional, but you can say that's why it is called the bipolar. So for laboratory purpose we will see this unipolar waveform. So that's why whatever waveform I will draw here, that will be unipolar in nature. Okay, because it is also possible. So it is also possible to draw non-return to zero signal in both unipolar and bipolar form, but I am only drawing the unipolar form because in laboratory whatever we will see in the CRO or DSO, that will be in unipolar in nature. The unipolar wave we will be able to see in the DSO. Okay, so that's why I am drawing only the unipolar waveforms. Okay, see now what is non-return to zero. First you have to understand it. For understanding, for non-return to zero, that means for 1 we will use some plus voltage, and for 0 we will use 0 volt, and plus voltage for total bit period. Okay, I am writing BP here. Throughout this bit period, whenever the 1 will appear, throughout this bit period we will represent this 1 with a plus voltage, and throughout this bit period we will represent the same 0 with no voltage or the ground line. That is the unipolar. That means if I draw this signal, you will be able to more visualize. So that is for 1 throughout. See, this is a bit period, right? This is a bit period. This is TB. This is 2 TB. In this way it will proceed 3 TB, 4 TB. This is a total bit period. Throughout the whole bit period, whenever a 1 will appear, okay, then I will represent this 1 by a positive voltage, and this positive voltage will be maintained throughout the total bit period. Again a 1 has appeared, so that's why again a positive voltage will be there. And whenever a 0 will appear, you can see that the 0 has appeared here. Then I will represent the 0 with no voltage or the ground voltage. Again a 0 has appeared here, then this voltage will be the ground voltage. Again 1 has been appeared over here. So what I will do for 1, I have already told you, the plus voltage will be represented, and this plus voltage will be maintained throughout the bit period. Okay, the dotted line, the gap between dotted line represents the bit period. Actually, bit period means for a single bit, what is the section, or in the time domain, what is the portion of the time domain is allotted. So this section of the time domain is allotted for a single bit, and this bit period is equal for each and every bit. You also know that. So for 1, the plus voltage will be maintained throughout the bit period. You can see the plus voltage has been maintained. Again for 0, a 0 voltage has been maintained, will be maintained throughout the bit period. For 1, again a plus voltage, positive voltage has been maintained throughout the bit period. And for 0, again a 0 voltage has been maintained throughout the bit period. This is the pattern that you can see here. That is actually 1 1 0 0 1 0 1 0. This is the pattern that has been produced over here. This is a one line coding has been done, that is unipolar or bipolar non-return to 0. That means this is the original data signal, original bit signal, original data bit stream message, original message signal, that is message signal means digital message signal. Okay, digital message means we have converted actually the analog message into digital form, whatever. So this message signal, we want to transmit this message signal in several types of waveforms or several kinds of line coding. Several kinds of line coding means several different types of waveforms. Okay, so this is a one technique number one technique where we can using this logical rule. For 1 we can transmit the positive voltage, and for 0 we transmit the 0 voltage, and these voltages that has been allotted logically, that will be maintained throughout the total bit period. That means throughout the bit period. Now the NRZ name comes, that is non-return to 0. That means why the non-return to 0? Because throughout the bit period the signal that has been allotted logically, that is the plus volt signal for 1 volt, throughout the bit period it is maintained, or you can say that throughout in between the bit period the voltage doesn't comes down or doesn't just vanished. Okay, doesn't fall down. Okay, or you can say this is a 0 line, right? This is a 0 volt line. So throughout the bit period the voltage doesn't suddenly falls to 0 or suddenly returns to 0. The voltage is not returning to 0 in between the bit period. That's why it is called the non-return to 0. Okay, very much interesting, right? Non-return to 0 means throughout the bit period whatever the voltage is has been allotted to represent ones and zeros or a single bits, different kinds of single bits. For this NRZ line coding technique, unipolar NRZ line coding technique, throughout the bit period the same voltage will be maintained. That means the voltage will not return to 0. So that's why the non-return to 0 has been mentioned, or has been, this name has been provided. Okay, for this type of line coding technique. Okay, now coming back to the second kinds of line coding technique. What is the second kinds of line coding technique? That is return to 0. Unipolar or bipolar. This is also unipolar, bipolar, both are possible for return to 0. For return to 0 I am writing here that RZ. Okay, whatever, we are considering here the unipolar waveform only, as in laboratory I have already told that we will see only the unipolar waveform. To match the theory with the practical, we are using the unipolar waveforms. Okay, so for unipolar waveform, what is the unipolar return to 0? What is the rule? The rule is almost same. That is, for 1 we will use positive voltage, and for 0 we will use 0 voltage. Okay, or the no voltage. But this positive voltage will be returned to 0 in TB. TB means in between TB the positive voltage will be suddenly returned to 0. Okay, that is the rule for the return to 0. How this is happening? If I draw this waveform, this will be more clear. Suppose for 1, whatever I have told, that is for 1 I will represent a positive voltage. Now this is a total bit period. For non-return to 0, this positive voltage will remain maintained throughout the bit period. But for return to 0, after some time this voltage will be suddenly returned to 0 in between the bit period. You can see the bit period has been finished here, but before finishing the, or before touching the bit period TB line or a single bit duration line, okay, or in between the bit period, the voltage has been suddenly returned to 0. Okay, that's why it is called the return to 0. Okay, that in between the bit period the voltage that has been returned to 0 suddenly, that's why it is called the return to 0 or unipolar return to 0. Why we are telling this is the unipolar return to 0? You can see that for this waveform also, for the previous waveform also, the waveform was distributed only the upper direction of the 0 volt line. Okay, that is the unidirectional. Okay, so that's why it is called the unipolar return to 0. And for next one, what we will do again, we will again start from positive voltage, but in between the bit period the voltage will be returned to 0 suddenly. For 0 we will represent the 0, and for 0 we will again represent the 0. For 1, again a 1 has been appeared over here. For 1, what we will do, we will start from the positive voltage, but in between the bit period we will suddenly return to 0. Okay, again for 0 we will represent this is a 0. For 1 we will represent this with positive voltage, but in between the bit period it will be again returned to 0. Okay, for 0 this will be 0. Okay, you can see that this is also the same waveform, that is 1 1 1 1 0 0 1 0 1 0, and you can already see that the pattern or the waveform pattern has been changed in some manner using this logic. Okay, now in between these two, if you use the return to 0 waveform, this will be very much difficult to detect the original or what the original waveform was. Original data was 11001010. If you got this waveform, if somebody who don't know what is the line coding technique that has been used over here, so it will be very difficult for him or her that this to extract this 8-bit data, because he will see the random waveform, this types of waveform is coming. So if he decode this data, that is he will get 1010 00 00 00 1000. That is the completely different data. If we normally decode this data, if we after seeing this waveform, if he or she, if anybody or the third party want to detect what is the original data was, he will get completely the wrong data, or the data he will also get that will be completely mismatched with the original data which was transmitted by this line coding technique, right? This is the main advantage. The rest of the two you will see, the another two types of line coding I will also tell you. For the rest two, you will also see that these two waveforms are completely different, and it is very much hard to extract the original data for these two kinds of waveform, which I am going to show you, right? So let's come back to the point, and the third kinds of line coding that I am going to use over here, that is Manchester. See, for Manchester there is no unipolar or bipolar, these two types of there are no differentiation, the unipolar or bipolar Manchester. That is Manchester is Manchester. There is no differentiation between unipolar Manchester or bipolar Manchester, whatever. This is the Manchester code, and this Manchester code is also called the biphase Manchester code. Why the biphase has been used? If we see the logic, it will be more clear. So let us see the logic first. See, for 1, listen to this carefully. For 1, plus volt to 0 volt. This is a transition in between a bit period in TV. In between the bit period, the transition should be used for representing a 1 bit. If the bit is 1, in between the bit period there will be a transition, that is plus volt to 0 volt. This plus volt to 0 volt transition represents that the bit is 1. Okay, and for 0 the reverse transition will be used, that is 0 volt to plus volt. Okay, when I will draw the waveform, this will be more clear, but for now I am writing here because I am trying to make you understand why the biphase term has been used over here. Okay, see, for one, we are not using a particular voltage. Here we are not maintaining a particular voltage, whether it is 0 volt or 1 volt. We will not maintain a particular voltage throughout the bit period for these kinds of line coding. What we will do here, we will make some transitions in between the bit period, or better to say that we will use some transitions that may be something from plus volt to 0 volt. It is a transition, or another transition that may be possible here, that is 0 volt to plus volt. In between a bit period, if there is a transition between plus volt to 0 volt, then you will say that this is a bit 1. To understand bit 0, you will see there is a transition from 0 volt to plus volt. Okay, as these two transitions in between a same bit period, two different kinds of voltage you will see, so that's why it is called the biphase. Why biphase? Because two different voltages in between TB. Okay, two different kinds of voltages you will be able to see in a bit period. So that's why the biphase term has been used. That is the two phases. Bi means two. Biphases, that is two phases. At a time, two phases will be seen in between a bit period. That's why it is called the biphase Manchester code. Now we will see how this code looks like. Now, the first bit is 1. Whatever I have told you, for 1 I will use a transition from plus volt to 0 volt, and this transition will be performed in between a bit period, that is in between this TB, in between this bit period the transition will be performed. See, the transition is plus volt to 0 volt. It is a transition. Don't think that in between for representing on 1 and 0 has been used over here. Yes, a plus volt and 0 volt, this positive voltage to 0 transition has been used for representing a 1. See, there is a next one. Again, for 1 we will use a transition that is plus volt to 0 volt. Again I am showing plus volt to 0 volt. This transition has been used. See, for 0, what we will use? 0 volt to plus volt. That is 0 volt, starting from 0 volt to plus volt. Okay. Again for 0, what we will use? 0 volt to plus volt. Okay. That is, for 0 we will start with 0, but in between a bit period there will be a transition to plus volt. And for 1 we will start from high voltage, and in between a bit period we will fall down to 0. So this transition, that is from positive voltage to 0, that is for 1, and for negative voltage to, or the 0 voltage to positive, that is for 0 volt to positive. This is for representing a 0. Okay, now you can easily understand whatever the code for this 1010 will be. That is for 1 there will be a plus volt to 0 volt transition. Again for 0 there will be 0 volt to plus volt transition. Okay, again for 1 there will be plus volt to 0 volt transition, and for 0 there will be 0 volt to plus volt transition. So this code, this waveform that has been formed here, this is for biphase Manchester code. Now you can easily just by visualization you can easily see that this code is much more difficult it is much more difficult to understand or to extract the original data, this data from this code, right? Because the formation has been changed a lot. Okay, the waveform for this digital data has been changed a lot in this code. Okay, so the Manchester code is the number 3, type 3 that we will use in the laboratory, and the last coding technique that we will use here, that is AMI, alternate mark inversion. This is very dangerous. It is very difficult to detect the original data from alternate mark inversion, because you will understand within a short period of time. Just let me rearrange these bit periods, because actually in alternate mark inversion, for same bit we use different marks. What is that actually? So what is the bit, line coding technique that I will use, that is the alternate mark inversion. See the logic. If first one, for first one that I will move from left side to right side, whenever first a 1 will be appeared or first a mark will be appeared, 1 is called a mark over here. For AMI, 1 is called actually a mark. See, two types of combination is possible in binary, right? That is 0 and 1. So we will not tell that 0 is a mark, okay, but 1 is a mark. So as the name itself suggests, alternate mark inversion. Why the name is like something like that, you will understand within a short period of time. So see, whenever first one will occur, that is, we will move from left side to right side, whenever a first one will be occurred, for that one we will use a positive voltage, and just after the first one, if the first one is occurred, first one is represented by the positive voltage, then the next one after the first one, that will be represented by a negative voltage, or vice versa. Okay, this will be much more clear when I will draw the waveform. Okay, actually what I am trying to do, see, suppose these ones may be continuously coming or not. If the first one is represented by the positive voltage, then the next one, see, this next one may be just after this, or maybe after some zeros also. If the first one is appeared, or the first one is represented by a positive voltage, then the next one will be represented by a negative voltage. Again, after this negative voltage, the one appearing after this negative voltage represented one, that will be represented by a positive voltage. See, after positive voltage there is a 0, and for 0 we will use 0 volt. Okay, for 0 we will use 0 volt. So 0 will be represented by 0 only, and for 1, see, whatever the last one be represented, we represented the last one with a positive volt, and the positive volt represented 1, whatever 1 will occur after this, that will be represented by the negative volt. After this, wherever the second one will be appear, that is, second one means second one with respect to the negative voltage represented one. The next one of this one, that is represented by the positive volt. You can see, alternatively, whenever ones are occurring, the voltage that are used to represent it is altering its polarity. That means sometimes a positive voltage is being used to represent a one, sometimes to represent the same one, that means same, not the same one, actually the same bit one, we are using the negative voltage. Okay, and how the positive and negative voltage, how you will understand when you have to use the positive voltage and when you have to use the negative voltage. So for that you have to look after the last one, that is what the last one was represented by. If the last one was represented by a positive voltage, then the current one or the present one will be represented by a negative voltage, or the vice versa. So let me draw these waveforms, then you will be more clear. Okay. See. See. So for this one, first one, suppose first one we are representing the first one with a positive voltage. Okay, see, as the first one has been represented the positive voltage, the next one that will appear, this one will be represented by a negative voltage. Okay, again the 0 for 0 I will represent it by 0 only. Again, and 1 has been appeared over here. Then you have to look after whatever the last one was represented. You can see before this one there was a 1 here at the second bit. For the second bit we have used the negative voltage, then we have to use the positive voltage for this one. And for again 0 is coming, so 0 will be represented by 0. And now this one has been appeared. Whenever this one will be appeared, the rule is always, I am telling, for representing this one you have to look after the last one. You have to keep your eye at the last one. For last one we represented it positive voltage. That's why we will represented this one with a negative voltage. And for 0 we will use 0, something like that. Okay, this is the representation for AMI. And why I have already told that the AMI is the most dangerous representation. Why? Because for 1 or for 0, whatever, we are not using a fixed voltage. Suppose it is not there that for 1 we are using a positive 5 volt, or for 0 we are using the 0 volt. It is not fixed. Sometimes for 1 we are using positive voltage, sometimes for 1 we are using negative voltage. So it is very much difficult to detect what is the actual data was from this AMI or the alternate mark inversion. Why the alternate mark inversion, that I have already make you understand over here. Okay, so in this way there are 4 techniques that I have shown you, that have been used here to represent this 8-bit data, and in laboratory the same 8-bit data will be used. So in laboratory, one more important thing, just a minute. In laboratory, as the DSO screen is very much small, what are the portion that you will be able to see? I am making you understand. That is, for NRZ you will be able to see this portion in a single DSO screen. Okay, in a single DSO screen. See, DSO screen is very small, so we cannot show the total 8 bits. Okay, so that's why in a single DSO screen for NRZ this portion will be represented. Okay, now for RZ pattern this portion will be represented a single DSO screen. that is the first 4 bit. Okay. Now for Manchester, just a minute. For Manchester, this portion will be represented, or this portion will be seen. Okay, this portion will be seen in DSO screen for a Manchester, and for AMI, this portion will be seen in the DSO screen. This portion will be seen in the DSO screen. So as the DSO screen is very small, so that's why I was not able to show you all the 8 bits. Okay, so that's why I have shown you part by part. Okay, you can easily compare. How you can compare? For this portion, you can, as the 4 bits the waveforms has been shown in the DSO, you can compare with the actual data bits. According to the actual data bit, see the waveforms, see the theoretical waveform, then you can match it with the practical ones. Similar for this also, and for this you can visualize this portion of the data, that is 100,101. For this portion, see the theoretical waveform, and then you see the practical waveform. If this is matched, then your experiment is successful. Okay, so I am now going to show you the waveforms actually, that whatever we have seen in the laboratory when we will perform, when we have performed the laboratory in the digital communication lab. Whatever the data, whatever the waveforms has been shown over here, whatever the green circle I have marked over here, the same circles or the same waveforms I will show within a short minute of time, within a few minutes of time, that has been captured by me when we were performing the laboratory experiment. Okay, so let us do it now first. And one more thing, before doing it, whatever you have to measure in the laboratory, let me show it first. That is, this is the lab trainer kit actually, and let me make you understand whatever you have to do in the laboratory. So this portion is not for you, so about this portion and this portion, these 2 portions is not for us, so don't worry about this circuitry, whatever the circuitry has been used over here. See, it is the data input select lines. There are total 8 datas that you can select by means of switches. Okay, just by turning the switches, just by toggling the switches, you can switch between the datas, that means ones and zeros. See, as I have already told you, okay, this is the D7 bit, that is the MSB, and this is the D0 bit or the LSB. Okay, so that means the bits or the data bits are starting from this direction to this direction. Actually, in theory, whatever I have already told you, I have taken a data that is 11001010, right? This is the same data. You can see one LEDs are glowing, means these bits are ones, so that means 11001010. Okay, starting from this direction. Why I am starting from this direction? That is, this is the D7 bit, this is the MSB bit, that is the leftmost bit in theory, and this is the rightmost bit, means LSB, least significant bit. Okay, so that's why 11001010. And one more thing, the first bit that has been used over here, that is the framing bit. I'll make you understand within a short, after making you understand the laboratory kit, that is why the framing bit has been used over here. Okay, that is, framing bit means this bit cannot be changed by means of switches. You can see that this is the 8-bit data, though this is an 8-bit data. The 7 switches has been present here, because through the 7 switches you can switch between ones and zeros from D0 to D6, but the D7 or the MSB or the fast bit must be a framing bit, and this mask should be 1. Okay, so that's why we cannot change the MSB bit, and we can change the other bits as well. Okay, this is very easy. So in laboratory, what you have to do, see, this is a clock input. Okay, this is a clock input. You have to measure the clock signal or the clock frequency. Okay, why you have to measure the clock frequency? If you measure the clock frequency, then you will be able to find the time period or the bit period, because depending upon the clock period, depending upon the clock frequency, the bits are changing. Okay, so that's why it is much necessary to find the clock frequency. Okay, in theory I have already shown you what is the bit period, TB. So to find out the TB, the clock frequency, determining clock frequency is very, very important. Though I will show you how the bits has been changed, or how the bit period has been determined from a clock signal. I will show you, because I have captured the total scenarios in the laboratory, so don't worry about it. But for now, whatever you have to measure, just listen to it. That is, first clock frequency has been measured. You have to calculate the frequency, and from the clock signal, if this is a clock signal, from the clock signal you have to determine the bit period. Okay, so clock frequency have to be measured. Now the data output will be the same data output, that is 11001010, and you will be able to see the waveform according to that normal waveform. That means whatever in digital electronics we were representing for 1, we used to represent positive voltage, and for 0 we used to represent 0 voltage. The same data that at previous of this session, before starting the line coding portion, I have shown you 11001010 equivalent digital signal. That digital signal, that is the normal digital signal, will be in the output over here. Okay, and you have to just visualize it, and this same digital signal is being fed here. Don't need to connect here, because this is internally connected. Okay, if this is not internally connected, you make sorry, this is not internally connected. Through a jumper you have to connect these two signals. That means you have to connect the data out and data in. That means the digital data, that whatever you have selected, that is the message data, now you have to do line coding. So that's why the digital data output will be connected to the digital data input of this line coder section. Okay, now measure only the 4 line coded outputs. That is, you have already know whatever the 4 line coding has been done theoretically, that is non-return to 0, return to 0, alternate mark inversion, and our Manchester code. So this is non-return to 0. Attaching this probe of the DSO with this point, you will be able to find the NRZ. Okay, these two are, this NRZ is not, you have to find this NRZ that I have already shown in theoretically, and match this theoretical waveform with the practical ones, that you will be more able to understand. This is the RZ, then this is the Manchester. Here, from here you will be able to find the Manchester, and from here you will find the RZ signal, and from here you will be able to find the AMI. These are the 4 waveforms that you have to see through, or you have to observe, you have to visualize the theoretical waveform that I have got with the practical ones, that you will be able to see in DSO just by connecting the DSO probe these 4 points. That means connecting DSO probe NRZ L, then RZ, then biphase Manchester, and then AMI. Okay, so now I am going to show you how the waveform has been observed over here. So let us see it now. Okay, one more thing, that is this is the thing that I have been provided. This is the basically from laboratory trainer kit. This picture has been captured. So here several kind for a particular digital data, several types of line coding has been given over here, but in between this we are concerned about this NRZ, RZ, biface Manchester and AMI. Okay, for this data that is 11000101, for this data the line coding has been done over here. Okay, so now I'm going to show you whatever the waveforms we have got and how the measurement has been taken in the laboratory. See, this is the clock signal, and you can easily visualize the clock period or the beat period. Whatever the clock period, that is equal to the beat period. Okay, and one more important thing, first thing that you have to measure the clock signal, right? So after measuring the clock signal, don't move the DSO frequency or the time per division probe. Time division knob of the DSO should be fixed throughout the whole experiment. At first, whenever you have to measure the clock signal or the clock frequency, at that time only you have to adjust the clock frequency such that at least 4 clocks are appearing in your screen. You can see the 4 you can see that the 4 signals or the 4th clock period, that is 4 beat period, has been occurred only here. That is, this is a 1 beat period, this is another one, this is another one, and this is another one. That means 4 clock period means our 4 clock cycles means our 4 beat period. That is, the out of the 8 data bits of the 8-bit data, the 4 will be measured according to the measurement of the clock beat period. That is, within this beat period the first data will appear. When I will show you the data, you will be more visualized. Okay, within this beat period the first data will appear. Within this beat period the second data will appear. Within this the third data bit will be appear. Within this the fourth data bit will be appear, and these are the 4 bits that the first 4 bits will appear of the 8-bit total data. And one more thing, the 8-bit data that we have considered here, that is 11001010, this is the repetitive data. Okay, so after 11001010, the same 11001010, that data bits will be repeated again and again. Okay, so adjust the time division and the x-axis knob of the DSO such that the first data bit, that is 11, must be appear in the first 2 bit period or the first 2 clock period. Okay, so this is the clock signal from where you have to measure the frequency. Okay, see, this is, what is this? Whatever I have already told you, this is the main data bit. Out of the 8 bits of the 8-bit data, the 4s has been appeared over here, that is 1100. Okay, and this is also the representation of the NRZ signal. The NRZ signal that I have already shown you. Okay, what is the NRZ signal? According to the NRZ signal, if you see the green circle that I have marked in the note, okay, this is the NRZ signal, the first 4 bit that is appearing, that I have already shown you. The first 4 bit, whatever the waveform we have seen in the theoretically, the same waveform has been appeared here. That is for first 4 bit means 1100. Okay, so this is for NRZ. Okay, and this is for RZ, that is the return to 0. For return to 0, I have already told you that there is a 1 to 0 transition, 1 to 0 transition for ones, and for 0 0 there is no transition. In theoretical portion, whatever the circle I have also marked with green pen. in the note, that is the for first 4 bit. Whatever we have seen in the theoretically, that same thing we can see in the practical also. It is for RZ. Okay, so let me show you the Manchester one. Sorry, what is the Manchester one? Just let me find just a minute. Yes, this is the Manchester code. That is for 1 we use 1 to 0 transition, 1 to minus 1, that is the positive voltage to negative voltage transition is for ones, and for zeros you can see from here the 0 transition has been turned on, that is 0 to 1, again 0 to 1 for zeros, 2 zeros, and here for 1 to 0 for first one, for second one 1 to 0, and for 0 to 1 for 0, 0 to 1 for 0, that is 1 1 0 0. 4 bits has been, according to the first 4 bits of the 8-bit data, the Manchester line coding has been done, and this waveform is also same with the waveform that I have already shown you in theoretically. Okay, and the last coding, that is the AMI. And before showing the AMI waveform, I want to make you remember that AMI waveform that I have seen in this DSO is the middle portion of the 8-bit data. If you kindly go back and see the green circled portion of the total 8-bit data, the same within this green circled portion, whatever we have seen theoretically, the same bit pattern will be appeared in case of AMI or alternate mark inversion. See, this is an AMI data, and I am again mentioning that this AMI data is not for first 4 bit. This is for the middle 4 bit, and for middle 4 bit I have already circled in the theory paper or in the notes. I have already circled that, I have already provided in the description. You can check it out. In the description, whatever the note I have provided, there in case of AMI I have also marked a green circle, and the green circle portion has been appeared over the screen. The green circles on the waveforms is representing that these are the portion that I have shown you, that we are able to see in the DSO. As the DSO screen is very small, this is not able to show the total 8-bit data, so that's why I have circled green in the theory paper, and this is the exact waveform that we have already seen in the theory portion of the green circle. Okay, so okay. And this is the last portion, that is 1100 was the first data, and this is the rest of the 4 bits, that is 1010. Our total data was what? 1100 1010. So 1100 data bits I have already shown you, and this is for 1010. This is the main data bit, and the line coded waveforms has not been shown for 1010. The 1100 for 1100 only the line coded waveforms has been shown over here, that I have already showed you. Okay, so whatever, I think you have enjoyed this and you have gained a lot of knowledge about line coding. That's all about today, and with this I am finishing our digital communication preface or knowledge about the laboratory. And this was the last experiment, that is the experiment number 6. Okay, so hope all of you enjoyed. Thank you, have a nice day. Hope we will meet you soon with a new video and with a new interesting topic. Okay, so bye bye everyone, take care, have a nice day.